Hello, this is Dr. Muhammad, and this is another video under the analysis of statically indeterminate structures. Today I'm going to talk about the second part of the continuous beam under the moment distribution method. We have started this method a couple of weeks ago, and we are talking today about the continuous beam too, because we have already talked about continuous beam 1. It was dealing with some hints of solving continuous beam using moment distribution. Today I'm going to talk about the settlement of support. Okay. So I'm going directly into examples because I think that we have enough information now and enough skills to solve the problems based on what we have learned in the previous videos. This is the example, one of the examples that is going to be explained today. In this example, as you can see here, we have a 3-span structure. It is fixed at A, and there is a roller at B and roller at C, and fixed at D. And the spans are equal here, 8 meters for each. The Young's modulus is given, and the inertia is given as well. We want to determine the member end moments for the continuous beam shown in this figure due to a settlement of 20 millimeter at support B. So here at support B there is 20 millimeter. As you can see here, it is 0.02 meter settlement support at point B. So we want to determine the end moments of the members due to this settlement of the supports, and we are going to use our moment distribution method. Okay, now let's go to the main steps of the solution as before. As we know that the first thing that we should always start with is the the distribution factors. We need to know the distribution factors at the joints that are free to rotate. So number one, we want to define what is the free to rotate joints. This is the first thing that we want to highlight. So as you can see here, we have fixed at A, fixation at A, and fixation at D. However, at point B and point C, they are free to rotate. So the structure can rotate freely at this joint C or joint B. However, here at joint A and joint D, it is fixed. So we have two joints that are free to rotate. This means that we are going to define the distribution factor on the right and on the left of each joint of the free joints in order to know how much moment is going to be distributed at the right and left, as we are going to explain. So this is the first step. The second step is the distribution factors. Which is we are going to make here. So the distribution factors are going to be determined at point B and at point C. So we will have two distribution factors, as you can see, at point B, which is DFBA and DFBC. BA, it is the left span of B, and BC, it is the right span of joint B. Similarly, we are going to do the same at joint C. So at joint C, we are going to have a couple of distribution factors. So one to the left and another one to the right. So we have CB, which is the left span, and CD, which is the right span. After that, we are going to determine the distribution factor. So the distribution factor, as we know from the previous videos, it is the relation between the relative stiffness of the member under consideration, which is BA here, we are talking about BA, or the span under consideration, over the relative stiffnesses of the spans or the beams framing into the joint. So if we are going to talk about the distribution factor for this span, which is BA, so it will be, in the numerator, it is going to be I over L. It is I over 8 here. L is 8 meters. Over the relative stiffnesses of the two spans. As you can see, the relative stiffness of BA, it is going to be I over 8. And the relative stiffness for BC, it is going to be I over 8 also. The far end in both cases, here it is fixed, here it is fixed. So we are talking about I over L. This is the relative stiffness. Okay, so this means that in the denominator it is going to be I over 8 plus I over 8, left and right. And then gives us, as you can see here, it will be 0.5. In a similar fashion, we are going to do the same for for span BC, which is this span. As you can see, the same denominator here will be repeated here or given here, and the top or the top of the fraction or the numerator is going to be I over L for the span BC. Span BC, I over L. Okay, so now this is the relative stiffness, and we can obtain 0.5 too. So we have 0.5 and 0.5. So the role of these distribution factors, as we said, it is going to give or distribute the unbalanced moment that is going to be developed at each point. That is going to be developed at each point. Okay, so that's the distribution factors at point B. Now let's go to the point or joint C. In a similar fashion, we are going to make the same. Actually, are going to find it the same, because here we have I over L, and here I over L. L here and L here, it is 8 meters, and similar also I, they are the same. So we will find that the same distribution factors as at joint B. So they are going to be 0.5 and 0.5 based on the same calculation that we have explained here. Okay, I over 8, and here I over 8 plus I over 8. So we have here the distribution factors now, and we are ready to go to the next step, which is the fixed end moments. These distribution factors, as we said, we are going to put them them here. Okay, so these distribution factors, CB, it is here, and CD, it is here. So based on that, we have done the first step in the moment distribution method. Okay, now let's go to the next, which is the fixed end moments. Now we want to get the fixed end moments. Actually, for the fixed end moments, we have drawn this shape. As you can see here, this is the deformed shape. We said that there is a settlement support 0.02 meter or 20 millimeter. We do not have any external loading. We do not have any distributed load or concentrated load. Just we have settlement of the support. So this settlement of the support is going to develop some fixed end moments at the ends of the spans. The spans that is joining at point B. So at point B, we have two spans, span AB and span BC. So this means that we are going to find fixed end moments to be developed at the end of span BA, which is this moment. We call it FEM, fixed end moment, that is going to be developed at point A. So we call it AB. And here we have a fixed end moment that is going to be developed at NB. So we are going to call it FEM, fixed end moments, BA. Okay. Similarly, also for this span, the moment that is going to be distributed here or developed here, FE, fixed end moment, which is denoted BC, and this one is going to be fixed end moment, which is CB. Okay, now we know that there are some fixed end moments will be developed. First of all, we want to know what is the magnitude and what is the sign or the sense of these moments. Now we can call or recall what I have explained like 2 videos before in the fixed end moments regarding settlement of the support. If you revisit the video or two weeks video, I think it is from 2 weeks, you are going to find that for the settlement of the support, if we have like fixed span like this, and there is settlement of support with magnitude delta at one of them, then the fixed end moments that is going to be developed will take this form. Take care in the right, I mean that in the point where that the settlement of the support occurs, the moment that is going to be developed is clockwise, as you can see. However, at the far end, the moment is going to be clockwise also. So they are having the same sense, which is clockwise moment. However, if the settlement is happening here at point B, we're going to find that the sense of the moment is counterclockwise at B, and here at A it is also counterclockwise. So the sense here is going to be counterclockwise. Okay? So we need to take care of this. Now for the span AB, this span, the support was from the right settlement. The settlement occurred at point B. This means that we are in this case. Right? So this is AB. This means that this moment, which is fixed in moment BA, is going to have this value and this sense, 6EI delta over L squared. Delta in our case, it is 0.02. Okay, 0.02. So this means that the value of this moment, which is going to be fixed on moment BA and fixed in moment AB, they are going to be having the same magnitude and the same sign. Okay, so we can put it like this: fixed in moment AB equal to fixed in moment BA, this one and this one, they are going to equal positive. Take care, because we said that it is counterclockwise, so this means that it is positive. In this case, it is going to be negative. So here 6EI over 6EI delta over L squared. So we have 6 E, it is given 70, I, it is 800, and delta, take care of the units, we have it in meter, so it is 0.02 meters. Okay, 0.02 meters. Over L squared, we have this span to be 8, so we are having positive fixed in moments with this value, 105 kilonewton meter. Okay, so this is the fixed in moment AB and BA. So directly we are going to put it in our table. So we are going to put positive 105 at point A and positive 105 at point B. Okay, so now we know about this and this. Okay, now let's go to the second span here, which is this span, which is BC. And this span we have fixed in moment BC and CB, right? This is BC and this is CB. And it applies with this span. So the moments, as we said, they are going to be with the same sense, which is clockwise, and it is going to be negative, right? And it will be 6EI delta over L squared. So they are going to be 6EI delta over L squared, but with the negative sign. Why? Because we said they are going to be clockwise. If we substitute here with the same delta, because it is the same point, then we are going to find that we end up with minus 105 value, the same as the previous AB and BA. So now we are going to put this directly. This is for CB and BC, so we are going to put it here at BC, minus 105, and CB it is minus 105. Okay, so now these are the fixed end moments which is the second step, fixed end moments due to settlement of support. Now the next step is going to be the most common moment distribution procedure, which is we have already the distribution factor here. We have the fixed end moments already. We have explained about them. Then we are going to use our method, the typical method, which is balancing the joints to be balanced in the same time. At point B, we have point B here, and we have point C here. As we said, we are going to balance the two joints together in the same step, in the same cycle. So when we look to point B, we will find that fortunately we have plus 105 and minus 105. Then they are balanced, so we are not going to make any balancing here. And for point C, we will find that 105 negative. However, here there is nothing because we do not have any loading at the last span. Remember that we do not have any loading at the last span here. So if we go back, this is the last span, which is span CD. We do not have anything here. This means that we do not have fixed end moments as well. Okay, so this means that it is nothing here, 0. Okay, so we do not have anything here for the span CD. Then this unbalanced moment need to be balanced using the distribution factor. So we're going to have to put here 0.5 and 0.5 with opposite sign, as we know well. Then we are going to draw this line. This means that the first cycle finished and make carryover. Through the line we make carryover. Half here because the far end is fixed here. And here the far end is fixed also. So here it is half here and half here with the same sign. 26 here and 26 here. Then you will find that in the next cycle we want to balance point B and C. So point B, it has 26.3. So we're going to give half here and half here using the distribution factors. So it gives us minus 13.1, minus 13.1. And we do not have anything here. So point C already balanced from the previous step. So we are not going to balance anything here. However, for point C, there are some carryover moment that is developed, has been developed here. So it is 26.3. There is no distribution factors here. It is the distribution factor as if it is 1. Okay, and here it is 1. So we do not write it because we know that there is nothing going to take place here and there is no carryover from it to the other joints. Now close this cycle by drawing the line and then look to the carryover. So here we do not have anything except minus 13.1, carry over here half and here half. Then you are going to have these two values. Then you are going to balance this amount of moment at point C. We do not have anything to balance here, so balancing this joint C, half here with opposite sign, and then draw this line and then make carry over half and half. Then you will find 1.6 here and nothing here, of course. Then you are going to find this 1.6 need to be balanced, so half here, and then draw the line again, and then half carry over moment here and half carry over factor here, carry over moment. And then we'll find that we need to balance point C, and we do not have anything at point B, so half here and half here, and then draw the line and then carry over half and half. You are going to find that we end up with 0.1, which is very small and negligible value. We can distribute it and then we can end the moment distribution process at this particular point, as you can see here. Then at the end, I think that you are familiar with this now. We are going to sum up all the moments at each point, at each joint from the left and right, and we are going to end up with checking from here and here. So we can check these moments, the summation, that they are going to be the same magnitude with different sign as a check for you. Similar here, same magnitude with different sign, and sum up all the moments at point C to get this value. These are the final step for us. This is the final step for us. Okay, now let's go to the next example that is going to make it clearer for us and a little bit complicated than the previous one. Suppose that we have a beam, as you can see it here, and this beam, it is distributed loaded with distributed load 2 kips per foot, and the spans are 20 foot each. We know Young's modulus and the inertia. It is given for us. And now we have two contributions for the moment distribution. First of all, we have distributed external load, and in the same time we are having a settlement of supports at point B, C, and D. So we have settlement of support at point B with 5/8 inch, and at point C 1.5 inch, and at point D 3/4 inch. So we are having settlement of supports plus distributed load applied here. So the main idea here that we are going to get the fixed end moment for the distributed external load and the fixed end moment also for the settlement of the supports, and then we are going to sum them up. That's the main idea of this example, that the fixed end moments are going to be summed up at each point due to the external loading and due to the settlement of supports. Okay, now let's go with the main ideas or the main steps that we know. Before going, I want to highlight something here. Whenever that we have the end spans to be simply supported, which is point D and point A, this means that the relative stiffness of this span would be, yes, 3/4 I over L. And also the relative span for this AB, it is going to be 3/4 I over L. Okay, this is number one. Number two, the far end is the far end is simply supported, means that we are going to make one-time balancing. Okay, only one-time balance, one balance only. Okay, and there is no carry over. No carry over. This would greatly simplifies the process. Okay. Also here we are going to make this for point A or joint A. It is one balance only, one balance, and there is no carry over as this one also. No carry over. Okay, that's it. Okay, now what are the free joints to rotate inside the beam? We have joint B and joint C. So we are going to make the distribution, moment distribution process on point B and point C to balance them together and carry over and so on. Okay, so only for point B and point C we need to have the distribution factors and so on. Okay, now let's go. And the first step, as usual, it is the distribution factors, which is going to be at point. First of all, we want the distribution factors at point, this is point B and point C, we are going to calculate in detail. But for point A and point D, the distribution factor is going to be given directly, which is 1. Okay, so put it as 1. This is the distribution factor at joint A and at joint D. Whenever that we have end support to be simply supported, then as we said, one time balance, no carryover, distribution factor is 1 only. Okay, now let's do the same procedure, or the common procedure for B and C. We are going to calculate the distribution factor at point B. We have two spans, left and right of point B. So we are expecting to have two distribution factors, dfBA and dfBC. Similarly, at point C, we are going to have dfCB and dfCD. Okay, CB and CD. CB and CD. Take care that I said that whenever that we have this span ending with simply supported, then its relative stiffness should be 3/4 I over L. Okay, for the simple support span, which is for span AB and for span CD as well. Okay, so this means that this span, it is going to be 3/4 I over L, which is 20, right? So it is going to be 3I over 80. This is the span relative stiffness of span BA, and also it is going to be the same for CD because we have the same span, so it will be the same. This is the value for the relative stiffness of the end spans because they are having, or they are ending with simply or simple supports. However, the member BC, it is the same. I mean that the same, it is I over L, which is going to be I over 20. Okay, because here it is as if it is fixed here and here, so we are using relative stiffness I over L equal to I over 20. Okay. Okay, now let's go and make the distribution factors as usual. At point B, we have 3I over 80, 3I over 80 as I have explained, 3I over 80. And the spans that is framing into B, it is AB and BC. So we have 3I over 80 for BA, and for BC it is going to be I over 20 as I have explained here. It is I over 20. The same denominator is going to be used here for distribution factor BC, and the numerator is going to be I over 20 because we are talking about BC, so it is I over 20. But for BA, it should be 3I over 80. BA, it is 3I over 80. And we can obtain the distribution factor easily. Apply the same process here for at point C. So this is at point C. We have CB and CD. In the numerator here, for CB, we're talking about CB. The numerator, it is I over L, which is I over 20 as we said. Okay. And for CD, it is 3I over 80. 3I over 80. And the denominator is going to be the same for both of them, which is at point C, it is the relative stiffness of CD, which is 3I over 80, this one, this, and the other one is I over 20, which is for CB, I over 20, and then repeat it here. Okay, so now we know well about the distribution factor of B and C. We can obtain them by simple calculations, putting the distribution factor at point D and at point A to be 1. Okay, now let's go to the next, which is the fixed end moments, the most important part for today, which is the fixed end moments. We have two types of fixed end moments. Fixed end moment coming from the support settlement, and we have fixed end moment that is coming from the external loading. We have external loading. So now let's get the fixed end moment due to the support settlement. So we have fixed end moments A and AB and BA. So we are having these AB and BA. If you remember what we have explained in the previous example, then for AB, this is AB actually, here we have AB. So the settlement at, actually our settlement not at A, it is at B. So we are using this shape here, okay, this formula. So fixed end moment at, if we're talking about this is A and B, so for A is going to be 6EI over L squared, and it is going to be counterclockwise. So this means that it is positive. Similarly, also for fixed end moments BA, it is going to be counterclockwise and the same magnitude. So they are the same actually. We said they are the same 6EI delta over L squared, and delta we have it with 5/8 inch here. Okay, so we have this amount of the fixed end moments with positive sign. Okay, now let's go with the BC. For the BC, we have settlement of support at B and settlement of support at C, right? So we are going to say, what is the differential settlement between the two? Differential settlement. Okay, differential settlement means that here we have 1/8 inch, means that it is as if it is 12/8, and we have here 5/8. So the differential settlement between this point B, and this point C, the differential settlement between them is going to be the difference, which is going to be 7/8. This is what is going to be used in our fixed end moments. So as if that we have, this is B and this is C. So here was 5/8, here settlement was 12/8. Then the difference between the two, is going to be 7/8. And it is from the right. So we are going to use also this shape here, or this formula. This means that the moment that is going to be developed here is going to be like this. It is going to be counterclockwise. This means that it is positive. And this is what we are doing here. For BC and CB, it is going to be positive, as you can see. This is 6EI as it is over L to the power 2. Okay, it is, we have 20, but we multiplied here by 12 in order to have the units to be consistent. Okay, we are having foot at the output. However, the input we have put, it is using inches. Okay, so now we use 7/8 inches, as we said here, as I explained it here and as I explained it here. Then you are going to have the sign to be positive and with this value. Okay, as I said, take care of the units. This 12 here, it is for the unit conversion, Okay, now the last one is this CD, and CD actually it has 3/4 at D and 1/2 at C. So the relative settlement between them is going to be 3/4, right? 3/4. So we will use 3/4 here, and the shape that is going to be suitable, it is going to be this shape, right? It is as if from the left. This is the span. If we say that, for example, this is span C, this is span D, for example, then at C happen the settlement, right? Then we are going to have clockwise fixed end moments. This means that it is negative. And this is true for fixed end moments CD and DC. They are going to be negative with the same magnitude, and we used 3/4. The 3/4 is 1/2 minus 3/4 inches. Okay, this is, as we said, the difference between the two. Okay, now these are the fixed end moments due to settlement of supports. We know them well, and we know them by the signs and the magnitudes. Now let's go to the next part, which is the fixed end moments due to external loading. Fixed end moments due to external loading. So we have 2 kips per foot external loading. So this 2 kips per foot, it is, we have AB and BC, and CD. They are going to be the same because the distributed load here, it is going to make some fixed end moments to happen like this. So all these moments, which is fixed end moments AB, BC and CD, they are the same magnitude and the same sign. So we equate all of them to be the same sign here, and the magnitude WL squared over 12, so it is positive. And for moment, fixed end moments, BA and CB and DC, they are going to be the same magnitude but with negative moment because they are clockwise. All of them, they are clockwise, right? So the same magnitude, they are going to be the same here, but the same magnitude but different sign, negative sign. Okay, so that's the case here. And then we have obtained the fixed end moments and the moment distribution factors, or the distribution factor. Then we can put the total. Now we want the total fixed end moments due to combined. That's important. This is the key feature of this example. We want the combined effect of the external load and the support settlement. So for example, at fixed end moment AB, it is going to be the summation. Summation coming from two sources here. Source that is related to the settlement of support, and another source which is related to the external loading. So let's have here, we have, this is 1,227 and we have 66.7. Okay, this is from external loading, this is from the settlement of support. So both of them, they should be summed up. 1,227.2 plus 66.7. This gives us 1,293.9 kips foot. Okay. In a similar fashion, we are going to do the same for BA. So for BA we have the same value here. Okay, but BA it is minus 66.7. So we're going to have 1,227.2 minus 66.7. Then it gives us the value here. This value is going to be here. This is BA. So it is 1,160.5. Okay. In a similar fashion also for BC, if we're talking about BC. So this is here BC. It is 1,000 something. Okay, and BC, where is BC? It is here. This is BC. So it is positive. So they are going to be added because they have the same sign, right? So it will be 17 like something, or 18, for example, if we're going to talk about BC, 1,784 something. Similar for CB. This is CB. Where is CB here? This is CB. And we have 1,700 something, and CB it is minus 66. So we are going to subtract this. They are having negative and positive, then the summation is going to be given as is, and so on and so forth with the remaining. Now the first step, the distribution factor ended, distribution factors, and the second step, which is the fixed end moments, already ended for us by obtaining these fixed end moments and putting it here with the sign, with the same sign in the moment distribution table. Okay, after that it will be pretty easy and simple for us to follow. The important thing to highlight that at point A and at point D, as we said, they are, if we go back here and see, they are simply supported, right? So in the simply supported, we put the distribution factor to be 1, as you can see, making only one time balance. Okay, one time balance, and then there is no carryover to it. As you can see, there is no carryover to this point. So I put it as a note here to remember it. Note that the joints A and D and the simple end supports are balanced only once. Okay, and that no moments are carried over to these joints. There is no carryover from this point B, for example, to point A, or from point C to point D. There is nothing here. Okay, so this greatly simplifies the process. After that, you are going to find that everything is being done as usual, and you can do it by yourself as in class assignment to exercise your skills in the moment distribution procedure. Okay, then you are going to sum up everything. Here the summation is going to be 0. That's right. And here also the summation is going to be 0 because we have simply supported at A and simply supported or simple support at D. Then we end up with 0. However, here we are going to end up with some values. You need to check them and you can do it. Please stop the video here and try to work out this moment distribution example and numbers by yourself, and check back again after coming back and checking the values. Now you are ready to have the home assignment, and your home assignment is this one. Please solve the moment distribution using the moment distribution method. Solve to get the end moments of this structure with two spans. We have different support, we have different external loading, distributed loading, and concentrated loading. We have only one joint free to rotate. We have fixed supports at A and C. E and I are given. The spans are given. So solve it and submit it to the iCampus. Okay, this brings us to the end of this class. Thank you very much and see you in the next video.